In this video, we'll be talking about how do you find the function of a circuit given the design of a circuit. And what we mean by that is how do you find the current that runs through every circuit element and the voltage drop across each circuit element. In other words, how much energy does the circuit is lost in a circuit element as the current travels through it. Because that's really telling you how the circuit performs. And there are two main tools to do this, and they're both called Kirchoffs rules. So he has two rules. The first one's termed the junction rule. And the junction rule relates how the current flows into and out of a junction of wires. So if you have a current flowing into some junction and current flowing out, Kirchhoff's rule says that the total current flowing into the junction is equal to the total current flowing out. So in this example where what I call I1, current 1, flows into this junction and 2 and 3 come out, I1 would equal I2 plus I3. And the reason is that there's no buildup of charge in these junctions or anywhere along these circuit elements. So if I have, say, 10 electrons flow into that junction, then there has to be 10 electrons that leave because I can't just keep piling up electrons at that spot. And I can't pull up more than 10 electrons because I can't deplete the electrons in that location. Now, it's not because it's physically impossible to do so, but because if you ever have a net charge like that, it'll have a strong electric field that it creates, and that will then effectively just take electrons from nearby objects or release electrons to nearby objects in the form of a spark, and be returned to a neutral charge. So on all of these cases, our circuit elements overall are going to be neutral. Now, another thing to note about using this is along a given wire, the current stays the same. Until you reach a junction, the current can't change. So all the way from wherever this wire started at some junction to the end where it met something else at ended at a junction, the current will continue to be I1. Now, Kirchhoff also has a second rule, which is termed the loop rule, and this is a slightly more algebraically difficult to use rule, but you're going to need to use both of these in order to find the currents in a given and voltage drops across the circuit elements in any given circuit. And the way to think about this, well, first I'll state this. So this Kirchhoff rule, as I stated, is that if I move around a circuit, I imagine just taking my finger and tracing the path that a current could take as I go around, that as I cross each individual circuit element, the voltage is going to change. So an electron would gain or lose energy as it flowed through it. So as I went through that circuit element, what I would find is there would be a voltage drop, and then I move my finger along this wire, come to another circuit element, voltage would change as I go through it, and I could look at adding up each of these individual voltage drops as I crossed a circuit element, and I could get, and in all of these cases, because current can't just begin or end, it has to come from somewhere essentially. Circuits are always in loops so that the current can flow around in a loop. And I can get back to my original location by moving around that loop. And what I find is if I add up all the voltage changes across each of the circuit elements, they sum to 0. And the reason why is voltage, kind of like height, depends only on location, not on path. What does that mean? So I imagine I'll use a more everyday analogy. Let's talk about you walking around campus or just in life over the course of a day. You start the day in your bed, you end the day in your bed, at the same location, and therefore at the same elevation. Over the course of the day, you'll walk up some stairs, so your elevation will go up. You'll walk down some stairs, so your elevation will go down. You'll walk up a hill, you'll go down a hill. You'll go up and down in elevation a lot of times. And you could keep track of how many feet you went up or how many feet you went down over the course of a day as you walked around whatever path you did. But if you began the day in your bed and ended the day in your bed, and your bed didn't move, so you went back to the exact same spot, then all of those changes would have to add to 0. If you end and start at the same spot, no matter how you got from that beginning location to that end location, all of the elevation gains would have to cancel out against all of the elevation losses to get you back down to exactly the same height. Voltage operates in exactly the same way. It's just a less intuitive quantity. So as the current flows around and goes and ends up gaining or losing voltage as it goes through each of the circuit elements, if it gets back to the same spot, it must have gained as much voltage as it lost as it went in that loop, because it's going to return to the same spot that has the same voltage. So we're going to take advantage of this fact by actually keeping track of each of these voltage changes and noting that they must sum up to 0, and then using that to find currents and voltage drops. And right now this will sound very abstract, and we'll look at how this actually shows up in a very concrete case very soon. Now, let's talk about how many times you can use these. In a given circuit, I'll go back to the first rule. There's a certain number of junctions. You'll count up how many junctions there are in an actual circuit. You can use one less than the number of junctions. So you can do all but one of the junctions, and these equations will be independent. What do I mean by independent? I mean, if you wrote down the equation for that last junction, you could have gotten the same information by just rearranging the equations you already had from the other junctions. So it provides you no new information. So here, with the loop rule, there's also a limit on how many equations you can write down before it becomes redundant. And the rule is not as easy to do to use as the as the junction rule, where it was simply you can count up how many junctions and do all but one of them. But here you just basically keep doing different loops where you now have a new circuit element that you're tracing the path through that wouldn't appear in any of the other equations. And as so long as you can continue to add new circuit elements, then you can continue to write down new equations. When you run out of circuit elements, then you've run out of equations. Now, when you do this, you have to be a little bit careful about whether you're going to gain voltage or you're going to lose voltage as you go through some of these elements. So, current physically flows in a certain direction, and as it goes through a resistor, it loses energy. That means that the voltage is lower on the, I'll call it downstream part of the resistor, the side that the current has already moved through the resistor. But I'm not talking about actually moving with the current always. I'm talking about tracing a path, which may happen to coincide with the direction of current, or may go against the current. Imagine like current was flowing water and you're walking beside the path of this river, and you can either walk in the same direction as the current or the opposite. You're just watching it and noting what happens as it goes through. So if you're tracing a path that goes in the same direction as the current and you cross the resistor, the voltage will go down. If you go in the opposite direction, it'll get higher because the voltage before the resistor is larger than after. And if you go from the after location to the before location, you're going to go to a location of higher voltage. Similarly with a battery, if you go in the same direction of current, you gain voltage because that's the purpose of them. And if you go in the opposite direction against the current, you'll lose voltage. Now, I'll often ask you to solve this current, and what I mean is I'll ask you to solve for the currents and all the different currents in here, and also the voltage drops across every single circuit element. And the way that you'll do this is that you'll find every place that has a common current, so any segment of wire with circuit elements along it that goes between one junction to the next. Write down that there's a current in that region, label it, like I1 for example. Guess the direction. It doesn't have to be right, but you're just going to guess which way it flows. Do that for everywhere in the circuit. Then you're going to write down a junction rule for every junction except for one, which relates the currents flowing into and out of. Then you'll go around a loop of the circuit, recording the voltage changes across every single circuit element until you reach the end of the loop, making sure that you use the appropriate sign for voltage increases or decreases for resistors and batteries that, as I mentioned before, sometimes are increases and sometimes decreasing, depending if you're going with the current or against it. And then you repeat that loop step, so you do it over a different loop, including some new circuit elements that you didn't use in your loop before, until you can't include any more circuit elements, or until you've reached the correct number of equations. Because you're going to need to know you need one equation for every unknown, and and the number of unknowns will relate to how many resistances you don't know, how many EMFs you don't know, and how many currents you don't know. And so if you add up all the unknown EMFs, resistances, and currents, and they equal, say, 5, you'll need 5 equations. Once you have that number, then what you do is you solve a bunch of algebraic equations for the values you want to know. And then when you get your current value, you'll interpret it in the following way. If you get a positive number for your current, that means you guessed the direction of the current correctly. And if you got a negative number for your current, that means you guessed incorrectly and it actually flows in the opposite direction. So then you can fix your guess that you made at the beginning of this step to figure out the actual direction that the current flows.